Let us continue our discussion on classical theory of radiation. So in this video we'll talk about Wien's displacement law, Wien's distribution law, this is energy distribution law, Rayleigh-Jeans law, then ultraviolet catastrophe. Okay, so these laws and phenomena that what we are going to study in this particular video, these are also very meaning historically it has got very importance in development, and you will see that these are the topics or the discussion that we will have under these headings had carried a historical importance in development of quantum mechanics or quantum physics. Okay, so let's start with Wien's displacement law. Okay, so before we go into that, we just to recap what we have learned in the black body spectrum. Okay, so first thing we have seen in the previous video that the energy distribution in the black body spectrum, which was experimentally observed. So these were the curves. Lammer and other scientists had done this experimental meaning the experimental study, and they had obtained these curves of the energy distribution of the black body at different temperatures. Okay, so first and foremost they have seen that energy distribution is not uniform over the wavelength range. Okay, so it has got a peak at certain wavelength, and that peak wavelength, okay, lambda m, which we had represented in the previous video, and so that this the wavelength corresponding to the peak of these curves, which we named as, or the where the energy distribution or the energy radiation is maximum, okay, that we termed as lambda m. So we had seen that this lambda m shift towards the lower wavelength in as we increase the temperature. Okay, in fact we have discussed this, that slightly I had mentioned about that lambda m, and if you multiply the corresponding temperature at which this lambda m was obtained, and if you you calculate lambda m for different curves and multiply by the associated or the corresponding temperature, it was observed that this lambda m into temperature, that the absolute temperature is a constant. Okay, so this was the observation, meaning they had got in their experimental results. Okay, and this was this comes under the law. Okay, so this is Wien's displacement law, which we will discuss now. Okay, so so it was all, see what after getting this experimental observation in the black body spectrum, then there were many people who were working like they were trying to find out a expression for obtaining these curves from the theoretical understanding. Okay, so which we will learn as we go forward along this video, and then also few videos after this. Okay, so Wien's displacement law, as I say, that this lambda m, which is the wavelength corresponding to the maximum of the energy radiation in the black body spectrum that we have seen, this lambda m is inversely proportional to the temperature, as you can see here. So if we all know all the in physics what we do, that if we have a proportional relationship, then you multiply by a constant, then you equate it, then you have a constant associated with that expression. Okay, so lambda m multiplied by t is a constant. That constant value is this 2. So constant we have written here as a b is equal to 2.892 10 to the power minus 3 meter Kelvin. Okay, and this is Wien's displacement law. Okay, so what you need to understand here is that, which was we have discussed many times in the previous video as well, in the beginning of this video as well. So as you increase the temperature, your lambda m, which is a wavelength corresponding to the maximum energy emission, so that lambda m shift towards the lower wavelength side. Okay, means in an experiment what happened, a blackened platinum was heated up. So you imagine, so if you are in the visible range, it must come from the, so if you slowly heat it up, it should become red, slowly sort of yellow. Okay, then as you keep on heating, it will go towards the blue, violet, and these things like that. Okay, so similar kind of experiment was done, and this you must have seen. If you take a simple rod and try to heat up using fire, you will see that slowly it will become red, then it will turn yellow. Okay, slowly if you heat even more, it will become, maybe blue if you heat up really up to high temperature. So this blackened platinum ware, when in an experiment, when it was heated up around 500 degrees Celsius or so, it becomes dull red. As you increase the temperature to 900 degrees Celsius, it becomes cherry red. Okay, and in around 1100 degrees Celsius, okay, it becomes orange red. Okay, if you heat up even more, it becomes yellow. Okay, and if you increase the temperature further, it becomes white. Now the question is, why does it become white? So you all must pause and think why it becomes. Okay, so let me give a explanation for that. What happens, as you can see the red, it is becoming, meaning within the red, you are seeing, as you are trying to increase the temperature within the red, it is becoming like shorter wavelength. Okay, it's coming from dull red is longer, and then cherry red is like little bit shorter than the dull red, then it becomes orange, then become yellow. Okay, so the peak of these curves, okay, so if you heat up like very high temperature around, let's say 1600 degrees Celsius or so, what happens, the peak almost goes beyond the visible range, so it enters the ultraviolet part. So what happens, the tail part lies in the visible range, isn't it? And so the tail part is the tail of this peak. Okay, so that intensity of this tail part is nearly equal, or you can approximate it, like all the colors are emitting nearly equal, like it's very hard to distinguish between different colors. Okay, so that's why it becomes white. Okay, I hope you got the point. Okay, so that's why if you this experiment actually proves that the statement for this Wien's distribution Wien's displacement law. Okay, so the lambda m multiplied by the absolute temperature is equal to meaning is a constant value. Okay, so Wien had also studied the energy emission at like the maximum energy emission. Okay, so while studying that, he realized that there's a relationship between this maximum energy radiation and the temperature. So apart from the wavelength, this EM is the maximum, this peak value of this energy emitted by the black body. Okay, so this EM which is the maximum energy, is proportional to T to the power 5. Okay, so and so we can write this EM equal to some constant multiplied by T to the power 5. Okay, so or in this expression EM is the same, like we have just shifted from the right side to the left side. So now you see you have EM to the power minus 5, which is constant. You have another expression which is lambda m. This is constant, but these two constants are not same constant. Okay, these are different constants. Okay, so what we can do now, see, you can combine these two expression. Okay, so or if I have to write this, EM is proportional to T to the power 5. Okay, where this is lambda m proportional to T to the power 5. Okay, so what can we do now? By combining these two, you see, so I can write that this lambda, so from here I can say that T is proportional to 1 by lambda m. So let's drop this subscript m. Okay, so I'll just simply write E and lambda. Okay, so the energy, so you can write energy is proportional to somewhat, we can write T, it's like lambda to the power 5. isn't it? Okay, so proportional to in that sense. Okay, so if I combine these two, what I can write, we can write an expression. Okay, so like this. Okay, so see, I am just, because I am writing the energy in terms of lambda, so that's why I have put this subscript lambda here. Okay, see this expression, you can see E is proportional to, like, you can write lambda to the power 5. So since we have to write it equate, so see, this is just, I am trying to combine these two expressions, but what exactly expression, I don't know. Okay, so the Wien was trying to relate these two expression. Okay, and where he had written that this E lambda, which is emissive power of the black body, which is equal to some constant, this is C is constant, and he multiply another function f of lambda t, which is function of temperature and wavelength. Okay, that has a maximum value at the absolute temperature T. Okay, so this E lambda is what? Emissive power of the black body that has a maximum value at the absolute temperature T. Okay, so he had got this expression. Okay, now see, idea is to meaning to find out, basically, see, if we in the current state we would like to have a like explicit expression for this E lambda, where we know what is this constant, what is the value of the constant C, and also the form of the function this lambda t, right? Okay, so what Wien did, actually, he did some arbitrary. So see, while these people are trying to like after so the people are trying to give an explanation for this black body spectrum which was obtained experimentally. So people are trying to put up a lot of theories, ideas, how exactly this why there is a peak, right? The energy distribution is not uniform. So they're trying to explain this experimental curve. So that's why, so to do that, actually we need to know the actual mechanism of this radiation, isn't it? So that's why this Wien was like with some, as we proceed, like a beginning of any theory that happens, you take some assumptions, you make some arbitrary ideas you put forward, then you slightly refine, and then you proceed, and then you see whether you are able to explain the experimental results or not, right? So following similar steps, this Wien had assumed some arbitrary and plausible assumptions. Okay, so he had taken up some arbitrary but plausible assumptions concerning the mechanism of this emission and absorption of the radiation. Okay, basically he made some assumptions where he said that this function f of lambda t should have the form a into e to the power a lambda by t, and this a, capital A and small a are two constants. Okay, so you will see later on, okay, these values will come up automatically when we study this Planck's law. Okay, so by substituting this form of f of lambda t here, okay, and this combine this constant C which we had assumed in the previous expression that we have talked about, A and C. So I have written this, combining A and C, I have written K. Okay, remaining things are as it is. So now just simply multiply by lambda d both sides just to represent that this is the energy or the emissive power of the black body within the short range of lambda and lambda plus d lambda. Okay, so energy emitted within that range, okay, given by this particular expression, and which is known as this Wien's law of energy distribution. So Wien's displacement law is different, Wien's law of energy distribution is different. Okay, so Wien's displacement law, not to get confused, is lambda m. Lambda m is the wavelength corresponding to the maximum at this peak of this okay, so lambda m is the wavelength corresponding to the maximum energy emission in the black body spectrum. Okay, so basically the wavelength corresponding to the peak of that curve. Okay, and that lambda m multiplied by absolute temperature T is constant, that is Wien's displacement law. Whereas Wien's law of energy distribution or Wien's distribution law, what it does is tries to explain this plot. Okay, however, what happens, this law holds good only for the region of shorter wavelength. So it could successfully explain the experimentally observed curve, okay, for shorter wavelength at low temperature, but it could not explain, or it did not obey for the longer wavelengths. Okay, let's see the plot which I have plotted here. Okay, so ignore this green color, okay, which will come up in like a very short while. Ignore the green part, and I have written this blue part is a Planck cloud, which is experimentally, here you can, this is experimental curve you can think about, okay, what people have observed in the black body spectrum. Okay, so there is your experimental curve, experimentally observe, experimental observation you can think about. Okay, so you can see for shorter wavelength, this part, this red and the blue is there is a complete overlap of this red and blue curve, right? So you see only one color because the blue is below underneath this red plot. Okay, so that's why you see only one color. Okay, whereas as you move somewhere this for the higher wavelength side, you can distinguishly you can see both this red and the blue curve. Meaning what is trying to show you here is that for higher wavelength, okay, this Wien's distribution law does not hold good. So it holds good only for the shorter wavelength. That's what it is. There is a drawback, or meaning you can see that the Wien's law failed to explain this the energy distribution in the black body spectrum for longer wavelength. Okay, so let us continue now. See, you will see very beautiful stuff here. Okay, so this Wien's law could explain the shorter wavelength side, whereas the Rayleigh-Jeans law, which we will learn just in very short while, could explain for the longer wavelength side, but none of this law could explain complete curve. Okay, eventually Planck had come up with a beautiful idea, okay, which led to birth of this quantum mechanics. Okay, just very meaning very intelligent and what should I say? It's a remarkable idea which could change the entire way of looking at this physics of this energy radiation. Okay, which we'll talk about. Okay, so let's continue. So then this Lord Rayleigh and James Jeans, these are two scientists. Okay, again they were trying to calculate, like theoretically calculate or theoretically make a contribution to understand this black body spectrum or the curves that we had experimentally obtained in the black body spectrum while studying the black body radiation. Okay, so what Rayleigh and Jeans, what they did around 1900, they were trying to understand, trying to calculate this energy density of the black body. Okay, what they consider in the theoretical model that this black body, like as we have seen in the earlier videos as well, so they have taken an enclosure, okay, which is maintained at a certain temperature, and walls of these containers are highly reflecting. So they and the idea was that this radiation inside this enclosure, which they thought to be a large cavity, like a cubical cavity, which is the size of, as it is shown here, size is, let's say, A is a cube, okay, very large cube. Okay, so within this enclosure, which is in cubical shape, this electromagnetic waves, they build up inside. Okay, so there is this like black body radiation inside. Okay, and they consider that this black body radiation inside this enclosure has got all possible frequencies. Okay, so moreover, what these walls of the, meaning so within the walls of this cubical cavity, this radiation build up a standing waves. Okay, so then moment you have standing wave, meaning then size of the cube or size of the cavity becomes very important, because what will happen, so depending upon the size of this cavity, okay, so whatever it may be the size, So it will this cavity will sustain only certain wavelengths, right? Meaning as we go forward, you will know why. So because there is a boundary conditions, right? So all this at the walls of the cavity, you will have only nodes of this wave. So the displacement at the walls, at that boundary of the walls, it has to be meaning the displacement of the wave or the disturbance that we talk about, it has to be zero, right? So it has to form nodes at the walls of the cavity. Okay, so that otherwise, meaning other see the waves that will not follow these conditions. So waves which will not form nodes at the walls of this cavity will not sustain longer. Okay, which will die down in as the time progresses. Okay, it will be, I think, more clear as we go along. Okay, so what happened? So so as I talked about this Rayleigh engines, their idea was that the radiation, they're comprising of the electromagnetic waves, the standing electromagnetic waves of all frequencies. So their idea was to calculate number of such standing waves in the frequency range of the nu to nu plus d nu. Okay, and then even after calculating, we will see how their idea was to get that curve. Okay, the black body spectrum, right? So in a large, so they considered a large cubical cavity with side length a, and then that a is much greater than the lambda, which is a wavelength of the radiation which is inside this enclosure. Okay, so this a size is much greater than the wavelength, that is wavelength of the radiation which are present inside this cavity. All right, so then as I said, these boundary conditions at x equal to 0 and x equal to 1 imply that, because the idea is, if you think just like 1D, okay, in one dimensional problem, so you have a fixed boundary, you have a string. What will happen? This wave or this string will sustain waves which has got wavelength. Let's say this is your string, so and this length is, let's say, L. Okay, so waves that will be sustained, the standing waves that will form within this string will have to have what? Lambda by 2 can be 1, right? So it can have only waves like this, okay, or it can have like this where lambda equal to 1, or I can write this lambda by 2 like this, right? Similarly, meaning it will sustain waves which has got, which has got integral multiple of half wavelength equal to the length of the string. Okay, the same case is happening here, but this is in a 3D like cube. Okay, it's a cube, so the walls of these cubes are acting like these boundary conditions as I've talked about in a 1D case. Okay, so that's what will happen. So here I will talk about only one dimension, and then I can extend the idea to the remaining 2 dimensions. Okay, so mathematically this is not very tough, okay, not very confusing, but only the idea it has to get clear. Okay, so you can, if you are not familiar with this standing wave concept, please go back and revise your understanding regarding standing wave, then it will become pretty easy to understand. Okay, so now considering that you understand what is standing wave, and then what are the wavelength that it can sustain in a string, okay, of length L, and it has been like it needs to form nodes at the 2 ends of the string and things like that, all these things. Okay, so now going forward, so if you have a boundary condition at x equal to 1 and x equal to a, so it can have, so this lambda x is wavelength, the wavelength of the wave along the x direction. Okay, so please don't get confused here. So if I take this boundary condition x equal to 0 and x equal to a, so it needs to have similar to what I have discussed here. So it will be lambda x by 2 should be equal to a in one case. Other case it could be like this, then 3. What I can write, I can generalize that n into, or I can say that n into lambda x by 2, like integral multiple of half wavelength. Okay, lambda x by 2 means I'm talking about lambda x is a full wavelength, and I'm talking about half wavelength, which has to be equal to the size of this cavity, isn't it? Okay, so and where this n goes, like n takes only integer values, okay, positive integers 1 2 3 4 5 only. So similarly I can have for remaining two directions as well. So nx multiplied by lambda x by 2 equal to ny lambda y by 2 equal to nz by lambda z by 2 should be equal to a. Okay, so I hope the idea is clear why these conditions are coming up. Okay, so now what will happen, so let me take help of these things. I need to have a 3D coordinate. Okay, now so imagine that this is your x-axis, y-axis, z-axis, and let's say this is your wave. Okay, which is coming up here. Now, so wave is so this wave will travel, it will, okay, like this, right? You can think about. Okay, so along the wave normal, meaning it's along the direction of propagation of the wave. Think about this wave is coming like this and okay, going towards the origin, let's say. Okay, so this is, so I am drawing only the one corner of your cube. Okay, so there is this cube all sides. So the wave which is like, let's say it's forming node here, another node somewhere here in the maybe in the corner. Okay, so this wave will make angle with the x-axis, which I will call it alpha. It will make angle with the y-axis, this is the black color, let's say. Okay, so this is beta. Similarly I will make with this gamma, z-axis. Okay, so these are called as direction cosines. Okay, so now what we will make some like mathematical analysis on this. Okay, so the if you see in the what is written on this slide, if the direction of propagation of a particular wave makes angle alpha, beta and gamma with x, y and z axis respectively, so what I will then, this lambda equal, so lambda is along this direction, lambda x is along the x axis, lambda y is along the y axis, the wavelength of this wave along the y axis, similarly along the z axis. Okay, so way it is done that your component along x-axis or y-axis or z-axis, okay, which is considered to be greater than this lambda. Okay, so that's why it's written in such a way that, okay, this lambda is equal to lambda x cos alpha. So this is I hope, okay, let me just put, so this is your alpha, this is your alpha. So you can make a right angle here. Okay, so this is your alpha, so this is your lambda x. Okay, so lambda x alpha will become this lambda. Okay, so this is your x-axis. So let's say you make a right angle triangle like this. This is your right angle, so this is your alpha. Okay, so this is your lambda x. This pencil here is a lambda x. So lambda x cos alpha will be lambda. Okay, okay, so similarly you can make this, you can try yourself and you can write it for lambda y. So lambda y will be cos beta, and similarly so I can write here that lambda will be for the lambda y cos beta and lambda equal to lambda z for cos gamma. Okay, so here you need to understand this lambda is wavelength measured in the direction of the wave normal, meaning along the direction of propagation of the wave. Okay, and other thing is this lambda x is greater than lambda. Okay, so it matters where you make this 90-degree angle. Okay, okay, so the spacing between the wave nodes. Okay, this is how you measure the now what should I call this wavelength of a wave. Okay, So just using this expression, this lambda equal to lambda x cos alpha, lambda equal to lambda y cos beta, and this, so I can simply write that lambda x is equal to lambda by cos alpha, lambda y equal to cos lambda by cos beta, lambda z equal to lambda by cos gamma. So from boundary conditions, okay, so boundary condition is what? Nx, right? Nx, lambda x by 2, all these things. So I substitute there. So n was equal to what? So nx, I'll write for only one, then you will understand what is it. Okay, a. Okay, so simply I have done what? This nx, then this is 2a by lambda x. I'll just written here. Okay, now what do you do? Substitute for that. Substitute for this lambda x, lambda y here, lambda z, because we all know what is lambda y, lambda z on top. Okay, so while doing so, you will get nx equal to twice a cos alpha by lambda, ny equal to 2a cos beta by lambda, nz equal to 2a cos gamma by lambda. Okay, now, okay, so we'll use this some expression from direction cosines. Okay, some like familiar expression of direction cosines. Okay, so if we simply this calculate this nx square plus nxy square plus nz square, and simply substitute this, you will get this. But we know that this expression here, this this part is equal to 1. Okay, so this holds good for this direction cosines. Okay, so then simply it will become 1. So nx square plus ny square plus nz square equal to 2 by a lambda to the power whole square. Then you all know that this lambda nu is equal to c, right? So nu is your frequency, lambda is your wavelength, c is the velocity of the wave. Okay, okay, so and then so it will be lambda equal to c by nu. So when I substitute this, it will be c by, c will come in the denominator and then nu will go on top. Okay, numerator. So this is simply just substitution and then arrangement, making things go left and right, and this is nu equal to c by 2a square root of nx square plus ny square plus nz square, and this happens for all positive integers of this nx, ny and nz. So remember, this n takes values 1, 2, 3, 4, 5, 6. Okay, no negative numbers. Okay, so I need to put a bit of attention to this expression, which I'll talk in the next slide. Okay, so as you all know that this nx, ny, nz can take only the positive integers, so the permitted standing wave modes can be represented as a lattice. Okay, so I can quickly have probably this. Okay, so if I have this, let's say nx, ny, nz, since this nx, ny, nz, okay, instead of taking 3D, let me take 2D stuff, then it will be much easier for me to explain, probably, I think. Okay, so I take this let's say this is nx, this ny, so there is the, let's say the z is going out of this plane of the screen. Okay, so the points here is that this nx take 1 and ny may take 1, it may take 2, 3, 4, like so. These are lattice points you can talking about, and this will be first octant of this the 3D space. Okay, in that coordinate system. Okay, so moreover, this expression, if you look closely, you will see that this is the expression for actually sphere, where your, like similar how like x square plus y square plus z square equal to r square, where the origin of your sphere, the center of your sphere is at the origin. Okay, so similarly here, which this expression within this square, that is your radius of the sphere. Okay, so going by that, so this will form, this equation gives that this is a sphere with a radius having 2a nu by c. Okay, but we must consider, because the n takes values only the positive integers, we must consider only first octant of that coordinate system, because if only if this n takes, or this nx, ny, and nz takes only the positive integers. Okay. All right. So what we are trying to do actually in this way, see, we are trying to calculate the number of modes of these waves, standing waves. Okay. So the number of modes of the frequency range we are trying to calculate. Basically, we are trying to calculate what here? Energy distribution of that. So first of all, we know how many modes are available, because see, once we calculate that, we will know the number, like average energy for each mode. Okay, things are coming up slowly, you will understand. Okay, so the number of modes with frequency range from this nu to nu plus the d nu, what will happen, because we know that this nx, ny, and z takes only positive integers, so I only and which lies only in the only the first octant, so I have to take the 1/8 of the volume of the spherical shell, because we are trying to calculate number of modes in the frequency range nu to, see, like nu and then d nu. Within that, how many modes are available, so we are trying to calculate that. Okay, so the spherical shell, so it's like, you know, the outer one is here like this, so radius of the outer one is what, your r plus dr, and the inner part is r. Okay, so this is your dr. Okay, so how can I calculate? So you calculate the volume of the outer sphere, then subtract the inner sphere. Okay, while doing so, after the calculations, you will remain with this. Okay, so already we have, since this r, see, we have substituted for r is this radius of the sphere, which is 2a nu by c. Okay, now you substitute back. Okay, while substituting, you need to calculate this dr, right? So r I can substitute for the r square, but dr I need to calculate. So while calculating dr, it's simple, right? So this a 2, all these are constant values, so dr equal to 2a by c d nu. So number of modes in the frequency range, so this expression, just substitute back, half, like pi by 2, then 2a nu, this part is r, this is substitution for r, and this is for dr. Substitute back, you will get 4 pi a cube nu square d nu by c cube. As you all know, this a cube is what? Volume of the cube. Okay, so substitute for that this v, and remaining keep as it is. Okay, now what you have to understand, the one thing, this number of modes for the waves. Okay, so because these electromagnetic waves are transverse in nature, and they vibrate in two independent direction. Okay, so independent direction means that two directions. So if it is propagating in z, so they vibrate along x and along y. Okay, so there are two modes corresponding to that. Okay, so that's why it's written here, as the electromagnetic waves are transverse in nature and vibrate in two independent direction perpendicular to the direction of propagation, so number of modes of vibration per unit volume in the frequency range, we have to multiply by 2, because these waves are transverse in nature and they vibrate in two perpendicular directions. Meaning if the wave is propagating in z, so these waves vibrate in x and y. Okay, so that's why I have to multiply by this 2 in front. So see here, we are trying to calculate this number of modes within the frequency range that we are considering, so we have to multiply by 2. Okay, so that is, so if I multiply by 2, then I will remain with 8 pi nu square d nu by c cube. Now number of modes we have got now, so now we have to we have to find out, or we have to know, meaning we have to get the average energy for each mode. Okay, so the average energy of each mode of vibration as per law of equipartition we know is half kT, but here I have written kT. Okay, so there within this also there are two things. So one half kT is for the kinetic energy part, and a half kT is for potential energy part. So that's why when we combine, the average energy for each mode of this vibration becomes kT. Half and half, this is kT. So the average energy associated with each mode of vibration is kT. So what you have to do now? Simply, energy density for the frequency range nu to nu plus d nu, we have to just, what will happen? We know the number of modes, then multiply by the average energy for each mode. As I told you, this is not half kT, this is kT. Half for the kinetic energy part and the half for the potential energy part. Okay, so the substitute whatever expression we have obtained, this n is what? Number of modes. So n of nu d nu represents the number of modes in the frequency range nu to nu plus d nu. Okay, while substituting, we got this the energy density for the various frequency rather I should say that energy density in the frequency range to nu d nu is given by this expression. Okay, so this is the Rayleigh's law in terms of frequency. Okay, so this is in terms of frequency. So if I have to convert this Rayleigh's law in terms of wavelength, what I have to simply this in place of nu, I have to substitute for lambda. Okay, how do I do this? This expression nu equal to c by lambda. Okay, and then you calculate d nu, simple stuff. After calculating, substitute back wherever this d nu and for the nu, and then you will get this expression. Okay, let me put a box around this. Okay, so this is Rayleigh's law for in terms of wavelength. Okay, so I already have shown you the plot for this, but let's then see if I have. Yes, I have this plot. So the Rayleigh's law and this Planck's law written again, this is experimental part. Okay, so this is experimentally observed. Okay, so you have seen that for the longer wavelengths, this Rayleigh's law holds good, whereas for shorter wavelength, so this, as we go to shorter wavelength, the energy density it tends to infinity. Okay, so that's why written here, this law holds good only in the region of longer wavelengths at higher temperature, but fails in the shorter wavelengths. Okay, so while deriving Rayleigh's law, the main idea was what? This Rayleigh engines, they have considered a cubical cavity, and then inside there is a radiations, and this radiation forms standing wave inside this cavity. So to calculate this energy density, what they did, first of all, they find out like how many, like in the frequency range of nu to nu plus d nu, how many modes it can sustain, or how many modes are present in that frequency range. Once we calculate out that, okay, using the technique that we have discussed in this video. Okay, so after that, we know that for each mode of vibration, how much energy is associated with that, because from the equipartition theorem we know that it is half kT. But here, because this here average energy for each mode is I have written kT, because half kT is for kinetic energy part, half kT is for potential energy part, so combining both of them, it becomes kT. Okay, so once you know the number of modes, once we know, then we have this average energy for each mode, combine both of them, then I know the number, the energy density within that cavity. Okay, what Rayleigh had considered. After knowing that, we have got an expression for energy density in terms of frequency and wavelength. And while plotting, we have seen that this law, this Rayleigh's law, the expression obtained to explain the blackbody spectrum, they have seen that this expression holds good for the longer wavelength part, whereas for the shorter wavelength part, it fails to explain. Okay, so it brings to another interesting topic, okay, which is known as ultraviolet catastrophe. Okay, part is that this, if you see in this plot, as you are coming to shorter wavelength part, or if I think about in frequency term, So shorter wavelength means higher frequency. Okay, so as I am coming towards the higher frequency side, your energy density increases. Okay, meaning with increase in frequency your energy density increases, or the energy emission by the black body increases, isn't it? So that's what this expression says from the, or that's the conclusion we can make from this Rayleigh's law, but which is practically not possible. Okay, this energy density increases continuously with increase in frequency and approaches infinity as the frequency increases infinity. See, one part is that this could not explain, this Rayleigh's law could not explain the black body spectrum. However, this is a very critical thing. This is a what should I say? This is not acceptable, right? If you increase the frequency, it's saying that if you have a black body, okay, and if it starts emitting higher, and so if you increase the temperature of this black body, it will start emitting radiations of higher frequency, and then it says that it will continuously emit such a like so much energy that it's practically impossible to get a like infinite amount of energy just you heat up the black body. Okay, so and moreover it contradicts the experimental result. Yes, also you will see that this will contradict the Stephen's law. Okay, meaning what? If I try to calculate the total energy, let's say if we, so this is energy density, right? So for a short range of this frequency, if we try to calculate the total energy density of the radiation as temperature T, by this expression, if we integrate out for all frequencies, you will see that this will approach to infinity. Temperature is constant here, right? So temperature of the enclosure is maintained at T, whereas the energy is becoming like tending to infinity. This is not possible, which is against Stephen's law. So Stephen's law also we all know, right? Energy release was which was equal to sigma T to the power 4, isn't it? Right? So here energy density is somewhat a finite value, but here it is going to infinity. So that's why, because as the energy becomes infinite, okay, which is not acceptable for, and then which violates the experimental results as well. So for all these reasons, so this is S. Okay, so this is known as ultraviolet catastrophe, meaning as the frequency increases, the expression of the given by the Rayleigh's law, the energy density approaches infinity, and which is not possible. Okay, and this is known as ultraviolet catastrophe, and they have named this particular that this is a catastrophe, because for a finite temperature your energy cannot be the total energy, if we integrate out for all frequencies, cannot be infinite. Okay, so this is what I intended to include in this video. Okay, so we will stop here.